In the last session, we discussed about the bidirectional sampling gate. That is, the bidirectional sampling gate is designed by using transistor as well as diodes. So in the last session, we discussed about the 4 diode sampling gate as well as 6 diode sampling gate as well as 2 diode sampling gates. So simply we say that the problem in the 2 diode sampling gate is the gain will be less. So simply we say that at the first level we use a transistor based sampling gates. The transistor based sampling gate, the problem is simply whatever the input signal will be applied to the transistor, that will be shifted, nothing but the output will be 180 degrees shifted from the input signal. The input is a sinusoidal signal with a positive direction, but the output is a sinusoidal signal with a negative direction. So there is a problem in the transistor based bidirectional sampling gate. At the same time, here there is chance of pedestal. Pedestal nothing but unwanted signal, nothing but whatever the input signal we get that, and remaining condition when the control signal is applied, whatever the input signal we get, and the remaining condition the output will be 0, actual condition of the sampling gate. But coming to this, pedestal will be occur. So this problem can be overcome by using 2 diode sampling gate. Simply the 2 diode sampling gate, here whatever the input signal we have to apply, that is produced at the output side. But the problem with the 2 diode sampling gate is simply the gain will be less. So in this session we discussed about the gain of the 2 diode sampling gate. So as well as what are the applications of the sampling gates. So what are the major applications of the sampling gates we discussed in this session. So this is a 2 diode sampling gate. So this circuit can be redraw like this. So by this circuit we have to simplify this circuit. So as like that. So that is here. So there is a chance of resistor, that is so simply the resistor, whatever the resistor we have to given. So that is I am treated with the R1. So that is R1 we have to redraw like that. That is R1 is R2 in parallel with RC. I am taking that way. That is R1 in parallel with RC, nothing but R2 RC by R2 plus RC. And at the same time here I am taking another resistor, that is R3 resistor. So R3 nothing but R1 and forward resistance of the diodes we have to consider. So that is R1 plus RF, and there is another term that is alpha we have to consider, that is RC. The whatever the output we have to take it, that is we take it as RC. RC by RC nothing but simply we say that this resistor we have to take it as a RC, and this one will be we have to take it as a R2. And in the diagram, so we take it as a R2 and this one will be RC. So simply the first term R1 is equal to, so R2 in parallel with RC, and R3 is equal to, what is the resistor R3? R3 nothing but R1 plus RF. That is this resistance with whatever the input resistance, that is forward resistance present. So that will be added, and there is another term that is alpha, which is the attenuation factor here, nothing but the gaining factor here. So that is alpha is equal to RC by R2 plus RC. So let us take these things from this diagram and redraw this diagram like this. So just redraw this diagram. Here I am taking alpha Vs, and here that one is 1 minus, that is alpha into 1 minus Vs, or 1 minus alpha Vs, and so this one I am taking it as a R1, and simply the diodes, whatever the diodes we have, that can be replaced with the a voltage, so that is V gamma. So whenever the diode is on, simply it can be replaced with the V gamma and the forward resistance RF. So that's why I am replacing this terminal, and this one is A and RF, and this one is V gamma. And again I have to represent that next side, that is another diode we have, that is V gamma and RF, and the next one is R1. And here also we apply the input voltage. So that is here we apply alpha Vs and 1 minus alpha into Vc. So that is 1 minus alpha into Vc, and Vc nothing but the control signal, and the same signals we have to appear here also, that is alpha Vs and 1 minus alpha into Vc. Here positive and negative and positive and negative, and this one is, and here there is a resistor. So that resistor we have to take it as RL, which is connected to the ground, and the terminals we have to take it as, here the terminal I am representing will be P, and so this one is P. So simply we say that what is the R3? R3 nothing but R1 plus R3. Sorry, R1 plus RF. So simply the circuit will be redrawn like this. This is, we have to take it as R3. And from this diagram, I'm finding the V0. So what is the V0? Simply we say that the V0 is appear here. That is alpha Vc. That is what is the alpha Vs into RL by RL. What is RL? The load resistor. So RL by RL plus R3 by 2. So nothing but here the R3 is in two parts. That is, so this resistance we have to take it as R3, and the total we have two R3s. So that is R3 by 2. Simply the V0 is equal to alpha Vs into, and alpha Vs into, there is a resistor here, that is RL by RL plus R3 by 2. Whatever the input voltage we have to give, that will be alpha Vs, where we have to find the output. Across RL only we have to find the output. Here at the both sides the output will be generally alpha Vc and 1 minus alpha into Vc. Alpha Vs and 1 minus alpha into Vc. At the same time, what is the A? A nothing but the gain, that is V0 by V input. A is equal to the gain, that is V0 by V input, and we find the gain, that is V0. V0 is equal to alpha Vs into RL by RL plus R3 by 2, and simply we say that that is alpha RL by, so Vs nothing but input signal, that is Vs cancelled. Why? Because we say that whatever the input signal we have to apply, that is Vs signal we have to give, so that is alpha into RL by RL plus R3 by 2. So this is the final output gain of this 2 diode sampling gate. As like that, we have to replace that one with so RC plus R2 and RL by RL plus R3 by 2. So simply this is the final output gate. So it is depends upon the RL and alpha and R3 by 2. R3 nothing but R1 plus RF. So simply we say that due to these diodes, the gain of the, so this particular 2 diode sampling gate will be reduced. So that is the major problem in this particular type. So this problem can be avoided by using 4 diode sampling gate. So at the same time, again nothing but compared to the 4 diode sampling gate, so the gain will be increased in the 6 diode sampling. So this is about the gain of the sampling gate, and the next one we have to discuss, that is applications of the sampling gate. So simply what are the applications of the sampling gate where we use this type of the sampling gate. So the major applications of the sampling gate are, so in our day-to-day life the sampling gates are used at the multiplexers. So what is meant by multiplexer? So it consisting of many inputs and we produce a single output. So simply the sampling gate, based upon the sampling gate operation, we say that we have one control signal. So at some condition, one of the output will be produced at the output side, and one of the input signal will be produced at the output side, and another control signal nothing but maybe the, so inputs we have 3 inputs like that, we assume like that. So the 3 inputs will be, so square wave inputs, let us take that one. So from this we say that at the first control level, that is first control signal, we apply a positive signal. During that time we have to say that the first V1 signal will be produced at the output side, and the next time, that is the second control signal, will be produced at the output side. We have to design this sampling gate like this also. And the next one is the sample and hold circuit. So what is meant by sample and hold circuit? For analog to digital converter. So obviously we use a sample and hold circuit. So simply it converts the analog signal to the digital form. So for amplitude conversion we go for sample and hold circuit, and for digital to analog converters, so that is whatever the digital signal we have to give, and that will be converted in the form of analog. So we go for the digital to analog, that is a sampling scope are nothing but sampling gates are used in the digital to analog converters also. And the very most important application of the sampling gate is sampling scope. So that is very important application of the sampling scope. And another important application is chopper amplifier. So in this session we discuss about the applications of this particular sampling gate also. The first application is a chopper amplifier. So what is meant by chopper amplifier? So where we have to use? So generally we have AC amplifiers and DC amplifiers. But why we go for the chopper amplifier? And what is the purpose of the chopper amplifier? Simply, so whenever the input signal is very less, my input signal will be very less. I want to amplify signal with a more amplitude. Nothing but the output of the signal will having more amplitude. So simply by using AC amplifier. So by using an AC amplifier, AC in that there is a chance of presenting a capacitor. So due to these capacitors, simply in this circuit we say that, so the capacitor effect, so due to this capacitance effect, so the output may not be amplified as we require. At the same time, in the DC amplifier also, we don't produce whatever the, so much more amplification is not performed by using DC amplifier also. By using AC amplifier, we don't perform that much amount of the amplification. Nothing but maybe the input signal will be within millivolts. I want to produce an output signal with a large amplitude, but it is not possible with the AC amplifier as well as DC amplifier. But by using the chopper amplifier, this problem can be overcome by using a chopper amplifier. So chopper amplifier amplifies as much as possible. So it amplifies the most of the amount of the input signal. So that is the major advantage of the chopper amplifier. Here that is the chopper amplifier circuit consisting of the resistor and the capacitor, and the output action is depends upon the switch action, that is S1 and S2. So simply the output is depends upon the switch action S1 and S2. Whenever the switch is open, that is S1 is equal to 0 or nothing but the S1 is open condition, then only the output signal, that is whatever the input signal we have to give, that is Vs signal will be produced at the input side. So in this particular time the V input is equal to V in. So in that condition only we give the AC V input signal to the AC amplifier. At the same time, so whenever the switch is closed, when this switch is closed, during that time, so the input signal will be simply when the switch is closed, the input signal will be 0. So whatever the input signal we have to give, and that will be grounded. So that is a major thing about this condition. At the same time in this circuit, so the capacitor and this resistor. So this capacitor and resistor is now the present case is called as a chopper. So chopper nothing but here when the switch is on, during that time the output will be 0. So in that particular time the input signal will be chopped, nothing but cut. So are removed like that. And when the switch is on, off, during that time only the whatever the input signal we have to give, that will be given to the AC amplifier. At the same time this action is majorly depends upon this resistor and capacitor. So this major action is depends upon this resistor and capacitor. At the same time, so these are known as a choppers. So in this particular time this is known as a chopper. At the same time, so here simply it performs a modulation action. So whatever the first I have to take that the Vs signal will be. So this is the input signal we have to given. So after that the the next one is chopped signal. What is meant by chopped signal? So in this particular time the average value nothing but so this signal is passing through this particular circuit. So simply we say that in this particular time the whatever the switch is closed, during that time we don't get any input signal and the remaining time we get the input signal. So that is a condition here S1 and so in this time that is S1 and S2 both are closed. So that's why whatever the input signal we have to give and will be chopped, and so this will be modulated. So that is signal modulated square wave when S1 and S2 operate synchronism. So in this technique, so simply we have to say that so whatever the input signal we have to give and at the same time we are also giving a square wave signal for the controlling purpose. So based upon that it performs this operation, nothing but it performs the modulation operation. So that's why this chopper amplifier is also known as a modulator. So by using this it performs the modulation operation. So that's why this is also known as a modulator. At the same time, so when S1 and S2 will be synchronized. So in the previous one we have to discuss that is both switch S1 and S2 synchronism. So that is very important for producing an output signal. So during that time only whatever the input signal we have to give and that will be produced at the output side. So that is very important. After that, so it is given to the a high pass circuit. So that's a low pass circuit. So a low pass circuit allows the low frequencies and reject the high frequencies, as we know that. So here we use a modulated signal. Whatever the modulated signal we have to give and that can be eliminated by using this low pass circuit. After this action, after completion of this action, so this signal, whatever this signal we have to give to the so a low pass circuit, it allows the low frequencies and reject the high frequencies, as we know that. So simply we say that in the modulation action, so the output signal will be only a input signal. So at particular interval of time. So that is about the chopper amplifier. So the combination of capacitor and this switch S2. Here the combination of this capacitor and switch S2 performs the demodulation. Here at input side we have to perform the modulation, and at the output side the combination of these capacitor and switch performs the demodulation action. So this is about the chopper amplifier, and another important application of this particular so sampling gate is sampling scope. So simply what is meant by sampling scope? So one of the very important application of the sampling gate is sampling scope. So here whatever the sampling scope displays the consisting of sequence of the samples. So simply it is like a CRO, but it displays the sequence of the samples. Whatever the input signal we have to give and that will be produced in the form of sequence of the samples. So that is very important thing regarding this sampling scope. And let us check the diagram of this sampling scope. So the input signal for this sampling scope is here we give the so at the same time here the input, here I am giving a comparator. So the comparator at the same time, sorry, the arrow mark will be in this direction, not this direction. And here I am giving a staircase signal. Staircase generator, and here I am giving a trigger pulse. At the same time here I am giving a ramp generator which gives a ramp pulse. And so this is given with the trigger. After that, so it compares. What is the purpose of this comparator? It compares the ramp input with the staircase signal. Whenever this staircase signal and ramp signal will be touches, so during that time, the whatever the input signal we have to give, and that will be produced at the output side. So that is a major function of this sampling gate. And after that, it is given to the sampling gate. So that is a signal, and after that we have to give to the stretch and hold circuit. So after that, this one is given to the vertical and horizontal display like a sampling scope, nothing but it is used for the display. So the horizontal is given to this by using staircase generator. The horizontal lines are given with the staircase generator, and the vertical deflection plates are given with the vertical deflection signals are given with this line. So simply the waveform will be the dotted lines 1, 2, 3, 4 and like this. So this is a circuit diagram for the sample and sampling scope. Here whatever the input signal we have to given. So simply I am giving a ramp signal and staircase signal. Both are compared by using comparator. So simply we say that so the input signal, first we give the triggering pulse. So first I am applying a triggering pulse. Like this. After that I am giving a, so that is the signal to be observed. Whatever the signal we have to observe, that will be given to this one. Nothing but we have to give a signal at the sampling gate. So that is very important. So that signal we have to take it like this. Whatever the input signal we have to given, that is given to the comparator. So the comparator having two inputs, that is a ramp like this. And after that I am giving a staircase signal. In this form. So in this condition, let us check the output waveform. Simply we say that whenever this ramp and staircase signal will be combined and nothing but compare, nothing but wherever they can be appeared. So in that particular time, so we have to generate the output. So simply we have to say that at the first condition the output will be here, and wherever it touches, simply here touch, the output will be second position, and the third position will be where it touch here. The third position will be here and here, like that. We have to produce the output signal, and after that it is given to the sampling. Just if this compares the input signal, and during that time whatever the input signal we have to given to the sampling gate, that will be given to the stretch and hold circuit. So this stretch and hold circuit gives the input to the, that is vertical deflecting plates, and this staircase signal, whatever the staircase signal we have to given for the time period operation, this will be given to the horizontal deflecting plates. So this is about the sampling scope and operation of the sampling scope. So up to this, the 6th unit is also completed, and thank you for the listening the videos. Thank you.